Hello everyone, welcome back to this channel and this series where we take electronic circuit concepts and demonstrate them in a practical manner to make what seems as an abstract idea in the field of electronics and electrical engineering and make it more tangible and easy to understand. This video aims to look at capacitors, more importantly, what time constants are and time constants in RC discharging circuits. This video is the second one of a mini-series that aims to take a look at time constants in RC circuits. The first video of this mini-series took a look at the time constant of charging RC circuits, and this one takes a look at time constants in discharging RC circuits. Before we get on with the video, if you'd like to support this channel, you can do so through subscribing and sharing this video with your friends. I also have recently joined Patreon, so if you'd like to support, you can do so through the link in the description. I'd like to also clarify that this video assumes that the viewer is familiar with capacitors and concepts in circuit connections, such as series and parallel connections. So if you'd like a refresher, you can check out the videos concerned with these topics in this playlist. So let's get on with the video, and let's revise what we learned from the last video. Electronics and electrical circuits may not always be in a stable or steady state condition, but can be subjected to sudden step changes in the form of changing voltage levels or input conditions, and that could look like just closing a switch. However, when a voltage or state change occurs, the circuit may not respond instantaneously to that change, and it may take an amount of time, no matter how small, if components like capacitors and inductors are present within the circuit. The change of state from one stable condition to another generally occurs at a rate determined by the time constant, which itself is an exponential value. The time constant of a circuit defines how the transient response of a circuit's current and voltages are changing over a set period of time. In this video, we will look at the transient response of capacitors and how much time is required for the capacitor to reach its discharged state or approximate discharged state when a path for discharge is created. So let's take a look at this circuit, and let's assume that the battery has been removed and the switch is closed. The capacitor would discharge itself back through the resistor in the opposite, and the current will flow in the opposite direction. So this is where we have a discharging RC circuit. As the capacitor discharges through the series resistor, the voltage across the capacitor decays to zero as shown in the figure. At one time constant, the voltage on the capacitor, which is denoted by Vc, will drop by 63% of its fully charged value. That means that the voltage Vc at 1 tau is equal to Vc at time equals 0 when the capacitor is just beginning to discharge and it is in its fully charged value minus 63% of that value. That means that the voltage on the capacitor at 1 tau is 37% of the voltage at its fully charged value, which is 0.37 of Vc. When the switch is first closed, the capacitor starts to discharge as shown. The rate of decay of the RC discharging curve is steeper at the beginning because the discharging rate is fastest at the start. But then it tapers off exponentially as the capacitor loses charge at a slower rate. The capacitor reaches discharge at approximately 5 time constants, where 99.33% of the full capacity of the capacitor is discharged. So now that we've observed the transient response of a capacitor getting discharged, or more specifically, we've looked at the voltage on a capacitor that's getting discharged. Let's look at an equation that describes that response and describes the voltage on the capacitor as it decays to fully being discharged. The voltage on a capacitor that's being discharged is equal to V, which is the supply voltage or the voltage of the capacitor at its fully charged capacity, into the exponential rate of negative t, where t is the elapsed time since the removal of the supply voltage, and RC is the time constant of the RC discharging circuit, where of course the time constant is equals to the resistance in ohms into the capacitance in farads for both charging and discharging circuits. Now that we've understood the behavior of voltage on a capacitor that's getting discharged, let's take a look at the current in a discharging circuit. Once the capacitor has a path to fully discharge itself, the current will flow in the opposite direction through the resistor. Therefore, as you can see in the graph, the current is negative. At the beginning, the decay of current to zero at one time constant, there's a steeper curve than at, let's say, 2 or 3 tau constant. And that is because the voltage discharging at 2 time constants is reduced. And of course, that would also reflect into the current. And at 5 time constants, the capacitor will have approximately reached its fully discharged state. Thank you for watching this video, and if you found it useful, consider subscribing to my channel, or if you'd like to support me, you can do so through Patreon, which you can find in the description below. Stay tuned for the next video, and as always, thank you for watching.